Hello and welcome to the Engineering Dynamics Course Companion. This is Class 23, continuing with kinetics of rigid bodies, and now we're going to deal with the rigid body impulse momentum method. That's right. This is Class 23. There's only one more class after this, so let's get over it. Now, if you want to get to the jump to the example, just go to the table of contents in the description below, and you can click on the time stamp when that shows up. Okay, so let's go to the bottom line up front. Well, we have a number of things that we want to take a look at and try to get a head around. Now, we introduced this thing called angular momentum that we define with a capital letter H, and we notice that this angular momentum has a vector hat on top of it. So it's a vector, an important thing to point out. And that's going to equal the mass moment of inertia times the angular velocity. Okay, so similar to the linear momentum, which was mass times velocity, now we have like a rotational equivalent, right? Where we have this mass moment of inertia, which is the resistance to getting it started spinning. And now it's times the angular velocity. So you could think of this as the attribute of a rigid body to continue spinning if it has started spinning. Or it's also its resistance to start up spinning, right? It's this momentum, right? And now it's a spinning momentum. We could also have an angular impulse, and the idea behind that is we have a moment, or a torque maybe is a type of moment that we could apply onto something to get for amount of time so we could get that spinning going, right? Or we could even have a force times the distance times that time, and that would create that moment, which creates a angular impulse when you multiply it by time. Now the angular impulse momentum equation now is the momentum before plus the angular impulse that gets applied to it equals the momentum after that's happened. We could also want to take a look, and we could say, well, we have about the center of gravity plus the distance to the center of gravity to the center of mass. The distance from the center of mass, the distance from where we're taking it about. So this is about point O, and so here is the position vector with respect to from point O to the center of mass, and we're crossing it against the mass time, the linear momentum right there, mass times the velocity to the center. And then there's the impulse, angular impulse added, and that's going to be here. So that's if there's multiple parts of the working together in a rigid body for the angular momentum equation. Angular impulse momentum equation. Now, when we have no external moment, or when the moment is actually internal, like if we define the system so any moments that are happening are equal and opposite inside the thing. So when there's no external impulse of momentum, angular impulse happening to it, we will now have the conservation of angular momentum, which is an interesting and useful principle to be on the lookout for in many different scenarios and many different fields and areas. Then we'll take a look at that. And then something we should also mind is that even though we have switched to the angular rotational version of things, in rigid bodies, we have translation and rotation happening at the same time. So while this is the rotational one, that translational one still applies. So that's that principle and those things can still be implied onto a dynamic scenario. So those are the tools. This is the toolkit we have available to us. We've added something new, but all the things we had before still work. Now, okay, so an angular momentum could be defined by a position, right, crossed with the linear momentum. That's one way we could define angular momentum. We can also say the angular momentum, let's say about the center of gravity, is going to be the mass moment of inertia times the angular velocity, right? So you could define it in either way. Let's say that maybe this is a particle that's part of the rigid body or made up of a rigid body that has a particle attached to it, that has a particle mass to it, or just an individual part small enough but it's attached by some distance r, and so that has a contribution to the angular momentum if it's whatever the scenario is. Or we could just take a look at the thing as a whole, as a rigid body, and we could find out what the angular momentum is right there. It could also be about some other point, by the way, and of course those points there. But here's about the center of gravity. So here's a newt dog, me, doing a cartwheel. I'm not going to try it. And you can see that they have the rotational angular momentum going on there and the translational momentum happening at the same time. And something is going to create an impulse, the angular impulse. Well, let's see what the linear impulse we defined as this IMP, and we with the subscript 1 to 2. It's taking place between two states. And that was going to be the integral of the external force integrated over time, right? And if we want to take the angular impulse, well, let's give it a character called ang-imp. And that's going to be the integral of the moment applied to the thing integrated over time, all right? If you have a constant load in linear momentum, right, or linear impulse, I should say. Linear impulse is just going to be force times that delta time if it's constant. And the same thing true if you have a constant impulse, right? So if a constant moment, excuse me. And so the moment doesn't need to be integrated, it's just delta t. Right. Now, impulse momentum applied to rigid bodies. Something we should be on the lookout here is we could say we draw a diagram just like we had in the other momentum method when we applied linear momentum in, I think, classes, I'm looking back there, I think it's 11, 12, and 13. When we applied linear momentum to various scenarios here, we made this diagram where we had the initial momentum that's happening onto the state, and then something happens to it, so the impulse happens to it, and that's going to equal the final state. So it's system momenta, the plural of momentum, plus the external impulses that are happening onto the system, and then finally the system, the total system momenta at the final state. And this can be expressed in two equations, although notably this is a vector equation. So within it we could break that down into components and have even more equations if that was relevant to the system that we were working on. And we might also want to rewrite this one up here and note that we could do it about some arbitrary point or about some important point to us. And then, as I had alluded to in the bottom line up front, we're going to take that r across the momentum of the center of mass. And that r is going to be with respect to the point about which we're taking the thing. And drawn to the center of mass. And the same thing true on to the second state. All right, now the conservation of angular momentum, that's another principle that shows up in a lot of different fields, especially in more complicated things. Something we want to be on the look for in like fluid mechanics and other areas right there in turbo machinery type of thing. That angular momentum is also some property that we want to look at. In the simplest of terms, if there just was one rigid body and it was spinning, right there, and let's go ahead and say it's spinning about its center of mass, or spinning about an axis that goes through its center of mass. We have the mass moment of inertia times its angular velocity is going to, at one state, is going to equal, and this should not be 2 right there. This shouldn't be a 2 right there. This is the same. Well, no, that's not necessarily true. I'm sorry. I'll take that back. We'll see what this means right here in a second, all right? That we're going to have the mass moment of inertia as at the beginning and its angular velocity multiplied by each other, and they're going to equal, if you were to change the mass moment of inertia of something by, like, maybe, as we're about to see, spreading our arms out or pulling them in, it would change what the final angular velocity would be. So we brought this up when we were taught in class 19, when we're talking about class 19, where you remember the ice skater was with her arms or his arms outwards, and they're using the tips of their skates to create a moment, right? So that they're applying their angular impulse, and they're getting themselves to spin with their arms wide out. Right there. As soon as they pull their arms in, they start to spin really fast. And that's the conservation of angular momentum. Here I'm having Newt Dog, me, on a chair with my arms out, right? So by putting my arms outwards, I've created a larger mass moment of inertia because my mass is distributed further out. As soon as I pull it in, I start to reduce my mass moment of inertia. So if I have a momentum, angular momentum with that large mass moment of inertia and are relatively slow, as soon as I make that mass moment of inertia small, I start spinning fast. Right? Now, an interesting aspect of this, let's see, I'm going to go back. An interesting aspect of this is that you might think that you could apply energy, right? The conservation of kinetic energy would, in this case right here, because there's going to be no change in potential energy when you're coming from here to right here. So you start to think that you could balance those things out. But it turns out that it doesn't work, because what you're doing when you're pulling your arms in is you're applying an external work into the system that's coming through the muscles, which is taking the chemical energy from the food that you've consumed right there, and you're bringing them in, and you're adding and you're putting energy into the system. So it's not going to balance out. That's an interesting part, because you have to remember that the conservation of momentum can exist and the conservation of energy not exist. Right? Those two things don't have to happen at the same time. All right, so here is a problem, an example, and I should, full disclosure, I found a mistake in the problem that's in the books, and I've corrected it here. So if you have the book, you should take a look at this, as you see, and I'll point out where that is. So Newt Dog, me, I'm rolling a bowling ball with some backspin, right? And so you could think of backspin as like, the thing is spinning, right? And it's spinning. But if it's rolling forward, it should be spinning this way. But backspin is rotating this way instead, and it's sort of slipping and skidding as it goes along. If you watch any golf, you might see, the really good golf players, golfers are able to backspin the ball and make it actually go backwards. But in this case, it's just going to backspin, and then the effort is it's going to slow down once the friction is sufficient to stop it, and then it's going to start rolling forward again. Right. So that's what's going to happen with this, where Newt Dog releases a 12-pound bowling ball. Which turns out to have a mass of 5.4 kilograms and a diameter of 218 millimeters, and has an initial velocity of 4 meters per second and an initial backspin of 8 radians per second. And the coefficient of friction, kinetic friction, is 0.1. Now we want to find the time that it takes for the bowling ball to stop slipping and the velocity when that happens. The mass moment of inertia for a sphere, we are told, is 2.5 mass times the radius squared, okay, because that wasn't given in the table provided in chapter 19. Okay, so we use that to find the mass moment inertia of the bowling ball, and then we make an impulse and momentum diagram of the bowling ball here. Okay, some things now we might want to have written out. The FBD and IBD would have been maybe. If we're going to be completely consistent here, we don't want to do anything on the right-hand side, whereas there certainly is going to be some amount of deceleration happening right here. Let's just, what we're really doing is, I'm drawing this for completeness, is in the y direction, right? We want to note that we have Fn and W, and there is some force right here, this F taking place. And of course, that's probably going to have a mass times acceleration into the thing. But we're really just going to write the thing out and to be able to find what the normal force is, the sum of the moment forces in the y direction. And we'd find that the normal force equals the weight. It's understood. And that ends up equaling 52.97 newtons. Now we have the kinetic friction will take place by multiplying the coefficient of friction by that. So we have 5.297. And when the ball stops spinning, we could take a kinematic relationship and say that this omega is going to be related to that final velocity by dividing it by r. That's not true initially. Remember, they're telling us that we've been given a backspin, which goes in the opposite direction of what you would expect it to be if it wasn't slipping. And we're given an initial speed, and we're given an initial backspin. So those are not related by that radius. But when it stopped slipping, yes, the angular velocity is related to the speed this way. All right, and so we write out our equation right up here. And here's where I made a mistake. Right, is I included this in the book, right? So I have just fixed it now on this slide, and we'll have to fix it in a later edition of the book. But being full disclosure right there, that we're going to take it about the center of the gravity. We're taking about the center of gravity, this angular momentum, and therefore, when we go up to this, we will have a force. Right, this force right here is causing times that distance right there times time, because it's an angular impulse, right? So we have a moment, this friction force times that distance right here, that distance right there, and then times time. So that's the angular impulse that's taking place. And then we start out with this angular momentum, and it's going counterclockwise, so it's positive. But we end up with this angular momentum, which is negative because it's clockwise. So you can see what's happening right there, right? And what I initially did was included terms in there for the mass times velocity about times the center of the thing, but that it's not needed because we're doing it about the center. If we were doing it instead about the point where it's touching the ground, then we would have something. But let's continue on here. So I put the values into this, and I believe I got them right, and I substituted this in for right there, right? And got some numbers, and here is equation 1. I'll call that equation 1. Now I can also want to apply linear momentum, right? So that was angular momentum. I can also apply the linear momentum to this. And so that's just going to be, and it's only in the x direction. That's that's the only thing that's happening, really, right? And you could see that we have initial momentum. Then we have this impulse that's happening due to the friction that's taking place, and we have a final momentum, right? And putting values into this, we have relation, we have time, and we have velocity. So you can see that we have these two equations, and we have two unknowns. Two equations and two unknowns. We can work with that. So I rewrote them out over on this slide, and then I'll solve for time in both of them, and then equate those two things together. And so because of that, I can now solve for my velocity. And I have a velocity. So it started out at 4 meters per second, and it's finishing up at 2.61 meters per second. That makes a pretty good amount of sense. It seems reasonable. Now I can go ahead and stick that velocity back up into one of those two equations, and I can find the time. So it's about 1.5 seconds or less than that. So 1/1000, and then it happens, right? It didn't make it to 1,000. So here is the answers for angular impulse and momentum, and also linear impulse and momentum. Those two things working together. So that was class 23, and now we're going to head to class 24. So for some more examples, get the Engineering Dynamics Course Companion, Part 1 and Part 2, available in soft cover and hardcover from Morgan and Claypool Publishers. You can go to the links below in the description to get to get to the publisher. Make sure that you subscribe to the channel. You can also go to Amazon, by the way, and find the book there. I've seen it. I've searched it myself. So thank you very much, and this is let's proceed on to the end of the semester class. Thank you.